Welcome back. This is session 6, and data preprocessing or data preparation is the topic of this session. We have spoken about different aspects of this process. Remember the pipeline. This pipeline needs to be always in your mind as a data scientist. Where is the data is coming from? That's going to be the raw data. Then you need to actually process the data and have it ready. Then you're going to apply your algorithm. Then you're going to visualize the results. And then you're going to make conclusion and results and decisions that you have to make at the end of the day. So we are in session 6. We are in part 4, where we are going to talk about the data transformation. So let's begin this section of session 6. In data transformation, we have many approaches. Some of the simple approaches, we are going to discuss them now. Imagine you have a data set and you already know the minimum and the maximum. This is the important condition that or assumption that you need to have in mind. You already know that the minimum and maximum, what is the minimum and maximum, reasonable minimum and maximum of that data set is supposed to be. Either you can rely on the reasonable minimum and maximum as an expert in the domain, or you're going to take a look at the data and say, this is my minimum and this is my maximum. The challenge of looking at the data and locating the minimum and the maximum is you could potentially be deceived by the outlier. Outlier data, which means it's just an extreme case that has gone on top, an extreme case that has gone at the bottom, and that's going to be your minimum and maximum. So that could be a challenge. You could potentially say, I'm going to first eliminate those outliers, and then I'm going to actually apply the algorithm that we are about to discuss. Either cases, the assumption is simple. The assumption is you have the minimum, the actual minimum, and you have the actual maximum. So it's known to you. And now you want to map this. You want to have, so this is, let's take a look at my finger. So this is going to be maximum, and this is going to be the minimum of your data. And you want to put it in the new maximum minimum, or you want to put it at the larger maximum and minimum. You either want to expand it or you want to contract it, but you want to do this in a linear way. So that's another assumption. We are actually doing a linear mapping between one data frame into a different data frame with a new maximum and a new minimum. So please keep that in mind. Now, if that is the case, the formula of this linear mapping is simple. You have the new maximum, you have a new minimum. This difference, of course, is going to show you the length, the bits. And then you have a new minimum as a constant, that's the line. But then you want to see where this data you're trying to map is resting in the existing data. So you're going to say, listen, I've got the data. I know what the minimum of the existing data is. I know what the maximum of the existing data is. I know what the minimum of existing data is. I just want to see where this data is resting in that frame. So I'm going to say VI minus minimum A, maximum A minus minimum A. That's the ratio. But then I'm going to map it into either expansionary scale or contraction way. I'm going to reduce the scale. So with that in mind, again, keep in mind, as a data scientist, you must be aware of the outlier that is happening in this case. Now, suppose that I have 12,000 and 98,000, and these are my income. I collected all the income, US Census, and I realized that the family income minimum is 12,000 and the maximum is 98,000. Just for the sake of my argument. Of course, what I just said is not correct. We do have CEOs who are actually earning a lot of money. But let's say that this is correct, 12,000 and 98,000. That's the data I would like to look into. With that in mind, I want to map it into 0 and 1. So those are going to be my new minimum and maximum. The way I'm going to do it is simple. Tell me where this data is resting in the existing data points that you have. So I'm going to say this, I'm going to scale it, and it's going to tell me where it is. So in this data frame where the maximum minimum exists, tell me where is this data? Where is the ratio that exists here? So if you tell me this ratio compared to minimum, then all I have to do is to add to the minimum. Now, the scale I'm about to have this is going to be between 1 and 0. And as you can see, this is 0.716 as the outcome. Now, if you wanted to try this a little bit easier, if you say that the minimum is 0 and the maximum is 100K, 100,000, then this would be a very easy number to see, 0.736. I could tell you. But this one, what does this one says? It says in this scale, the salary of 73,600 is actually 0.16. So between 0 and 1, 0.16 is going to be a little higher and closer to the maximum, which is 1. And that's true, because 73,600 is closer to 98,000. So this is a normalization, and this normalization is called min-max. And min-max means you have a minimum, you have a maximum, and also another assumption is it is a linear mapping. The other one says, okay, listen, I'm an expert in the domain. I have done this sample many times in my life, in my career, in that frame of 2 years, 3 years, when I have been facing these experimentations. And then I realized that the sample has a mean and has a standard deviation. And so the mean is noted as A bar, and a standard deviation is noted as sigma A, and then I have the data. So the question is, if you know what the mean is, if you know what the standard deviation is, and remember we are talking here about 1 sigma, you could potentially have 2 sigma and 3 sigma in mind, but at this time 1 sigma is the majority of the data. Remember that. The beauty of this approach, by the way, is that you are not going to be deceived by the outlier. The outlier is 3 sigma, 4 sigma. Remember the normal function? 3 sigma, 4 sigma on the edges of the normal function. That's the outlier to us. So what we want to do, we want to just get a sense of what the value is compared to the mean versus the standard deviation that we have. So let's take a look at this example. We took a consideration of the USA family income. The average family income is 54K, and the standard deviation is 16,000. This is correct, irrespective of whether you are going to include the CEO, millions of dollars of income and billions of dollars of wealth. That doesn't count because they are outliers. You and I, as regular citizens and people of a country, obviously, we have a regular range of salary. Now, I want to know where this one is, 73,600. I want to know where is it. So I'm going to see 73,600 versus my mean. So I want to see the distance with the mean, 54,000. And then I'm talking about 1 sigma. 1 sigma is the majority of the data points supposed to be. And then I'm going to be 1.225. So that's what this one is going to say. So 54,000 and 16,000, what do you get? If you add it, if you add 54,000 and 16,000, what do you get? So 6 and 4 is 10. This is going to be 70,000. So what does this simple equation tells you? It says that 73,600 is 1.225 sigma away from the mean. And that's all you need. You're going to say, okay, 1 sigma and then 2 sigma. You already know the data scientist vision of a normal function, and 3 sigma. You're going to say 1.225 is out of 1 sigma, but not far enough to say 2 sigma. That's what it says. There are times that you want to normalize it using decimal scaling. So it's simple. As an expert in the domain, you're going to say, I know what the minimum is supposed to be. I know what the maximum is supposed to be. I just simply want to have a decimal point. So for example, you have minus 986 and you have 917. You take a look at the absolute. And if you take a look at the absolute, you're going to say, listen, my knowledge tells me that the minimum maximum is supposed to be minus 1,000 and plus 1,000. If that's the knowledge you have, you're going to have 1,000 means 10 to the power of 3. So this is going to be 10 to the power of 3. And then you can potentially scale 986 and 917 to 10 to the power of 3. They are going to give you fractions, minus 0.986, plus 0.917. What does that mean? There are many, many algorithms that are going to behave strangely if, in a very strange way, if the data points are extreme. I'm going to give you an example. For example, Bitcoin. If you take a look at the rise of Bitcoin in price, you can see that the Bitcoin often goes exponentially. And if you just want to give that to any algorithm, the algorithm might be inaccurate. Of course, Bitcoin and Bitcoin exchanges are different types of environment. We know that there are basically information available to some of the people, or perhaps a player himself or herself knows what to do. A whale, we call them whale traders, and then they could potentially flood the market with the coins and take away the coins or buy the coins or sell the coins. We know that, right? So the issue is this: if the data is extreme, you don't want to even do linear mapping. You want to do nonlinear mapping first. So you could potentially apply a log function, logarithm. So for example, log of 10, usually we do log of base 10. And therefore, the signal becomes a little bit tame. A wild signal becomes tame signal. And then you could potentially even do normalization that we have been discussing now, as in linear normalization, okay? So keep in mind that there are times we have to be very careful about the nature of the data. And you are supposed to be observing the nature of the data before you apply any sort of data transformation techniques. And there are many, as we have discussed so far, and there will be some more to come. For me to discuss the discretization, I want you to alert you to this figure. So this is a figure. There are some important information on this side, on this slide. We have different types of attributes. We have nominal or categorical, and for example, gray, blue, red, that's one of them. Ordinal, for example, academic rank, assistant professor, associate professor, professor, as a student, undergraduate student, master student, PhD student, postdoctoral fellow, associate, research associate, and so on. In terms of real numbers, of course, something like age. Age is supposed to be a number. As well, depends on how you want to basically categorize age. If you wanted to say young and old and middle age, that's different. But when we say number, of course, it's going to be numeric, and that's an attribute we could potentially have in the data sets. Or create using the existing birth of date and today dates. You can simply subtract and get the age. There are times that the data is supposed to be continuous. We do have continuous data, for example, the temperature. But keep in mind that the temperature that is obviously the ambient temperature that is outside, it is continuous. But as soon as you start measuring it, it becomes discrete. Because obviously you can't say outside is 2.9 and then 2.99 and then 2.91 and then 2.912 and so on. You see the number, for you to have the continuous numbers, you need to go into every possible number between 2.9 and 3. And that's not possible with our measurement tools, okay? Keep in mind that in many cases, you can't even have a decimal number anyway. For example, if you are trying to take a look at the polling of an election, you can't just say, I just ask 1.2 people about their priorities. There is nothing called 1.2. You have either one person, or you have two people, or you have three people. There is nothing called 1.2. It doesn't make sense, right? So there are times that you need to consider the data that is most often analog in the form of a discrete. So take a look at this signal. This is an analog signal, and then I'm going to discretize it. And the way I'm going to do it, I'm going to actually consider a rectangular in mind. Now, this rectangular are similar to a bar chart. This is not necessarily a bar chart, but in the bar chart, we discussed in one of the labs how this binning or rectangular is supposed to be designed. So with that in mind, what is this? So take a look at this bin. So this bar, I would call. So this bar, this is whatever is on this edge and whatever on in this edge, I'm going to actually represent them by a flat line. Flat line. So analog and then flat line. Now take a look at this one. Anything on this edge, anything on this edge, I'm going to go by a flat line. And this one, anything on this edge, so point, take a look at my cursor, and then anything on this edge, another cursor I have, is going to be a flat line. You are going to have error. Of course you are going to have error because you are discretizing the data. And the way you could potentially minimize the error is to make your width a smaller and a smaller and a smaller, the resolution. And the resolution, the smaller it is, then the smaller these gaps will be. It will be to an extent that you would not be even able to distinguish between discretized data points versus the analog data points. If you make it 0.005 as the width of your bar or rectangular that we are talking about, then it's so small that the eyes cannot see the difference between the discretized data point as well as the analog data point. So this is very important for us to see what we are trying to do. We are going to introduce a bunch of error. We could call it rounding error. We could call it, you could potentially consider those type of errors, but eventually we are going to make it simpler for our own algorithm to investigate the data. We have two types in this presentation of discretization. We have equal width and equal depth. Equal width is about distance and equal depth is about frequency. In equal width, I'm going to take a look at the data frame, the minimum and the maximum, and I'm going to divide it into interval. So say I want 2 interval. So I want to alert you though, keep in mind, for example, if I say I want 2 interval, what does that mean? You could have a data here, then you have a data here, and then you have a data here. If I say 2 intervals, I might be referring to 3 data points. Interval means a width, a length that I need to have. So that length could be a fixed number. And the way I'm going to do it, I'm going to find the highest value of the data point. I'm going to find the lowest value of the data point, b minus a, and divide by n, the number of intervals you want. And that's going to give you the width of every rectangular or bar chart that we had in the past. Now, in the previous slides. Now, frequency on the other hand says, listen, I just want you to tell me about how many points you want me to have in each bin. Let's take a look at an example here. So this is an example we discussed in the past, and we had these examples done, I think, in previous sessions. I want to divide it and partition it into equal bits of 3. So what's the maximum? 34. What's the minimum? 4. So 4 is here and 34 is here. And I want 3 intervals, 3 bins. So 34 minus 4 divided by 3, that's 10. So the way I'm going to do it is simple. In this case, the way I'm going to do it, I'm going to start from 4. 4 plus 10, 14. So anything from 4 to 14, I'm going to write it down here. So anything from 4 to 14, I'm going to write it in this one. So that's 1, okay? Then the next starting point is going to be 15. Right after 14, it's going to be 15. It may be part of your data set, or it may not be, but doesn't matter. 15 becomes your initial point of the second bin, plus 10, 25. Anything from 15 to 25, including, of course, the last bit, which would be 24, is going to be here. So keep in mind, we said 15, and then 14 is outside of the bin. 4 plus 10. Remember, as I said, we are talking about the bin. You could potentially say 4 and 10, 14. So I'm looking at 4 and 13. Then when you say 15 and 24, you're not looking at 25. You're excluding that 25. You know what I mean? So when you say 25 and 34, you could potentially exclude the 34. There is a bit of a typo here, and we need to be careful on that. Okay. So 4 and 14, that's one. 15 and 25. So if I wanted to say 25, this would have been on this side, and then 26 and 36 would be the next bin. You just need to be aware of how you're doing this so that you remain consistent and fair. So if I say 4 plus 10, 14, and 14 is excluded, 15 plus 10, 25, and 25 is excluded, 26 and 36 and 36 is excluded. That's how I'm going to do this binning. That is equal width binning. Now, equal frequency binning. Now, take a look at this one. The way I did the binning, I had 3 numbers, 4, 8, 9. But the last bin, 25, 26, 28, 29, 34. So therefore, it's not of equal number of balls in that sense. Now, here I'm going to say equal frequency. What do I mean by this? So how many points do you have? You count the number of points and you say, I want this to be equal number of the balls in every bin. So I have 4 number here, I have 4 number here, and I have 4 number here. And I don't care where they land. They could potentially land on extreme edges, but that's okay. I just want to have equal number of balls in each bin. Okay, with that in mind, I'm going to close this this session, and I'm going to have my session number 6, part 4, and I'm going to discuss about part 5 and follow-up files in a moment. Thank you very much.